Thank you for watching this video from Spenigo Software. For some background information, Ubuntu from Spenigo Software uses Logical Volume Manager, or LVM, for storage administration. The database partition and the data store partition in Ubuntu use LVM. This video is an effort to share our knowledge of LVM in an easy-to-understand manner for the community at large. We introduce LVM and the commands used to manage LVM in a Linux server environment. Since production Linux servers are typically headless and terminal-based commands are used in such instances, we follow this approach. Initially, we will take a look at legacy disk partitioning and some related issues. Then we introduce LVM to illustrate how these challenges can be handled by LVM. Along the way, we will discuss the concepts and commands in LVM. And for a little bit of history about LVM, according to Wikipedia, Heinz Malzhagen wrote the original LVM code in 1998 when he was working at Sistina Software, taking its primary design guidelines from the HP Unix's volume manager. Now let us take a look at the legacy or traditional Linux disk partitioning. Consider a fresh new disk that is out of the box to be used for the very first time. The disk has a number of blocks of bytes. If a disk has 256 gigs capacity, a user may be interested in using 64 gigs for /root, 64 gigs for /var, and 128 gigs for /usr/local mount points. In this case, the disk can be divided into three sections of 64 gigs, 64 gigs, and 128 gigs, each of which is called a partition. Essentially, a raw disk is divided into slices called partitions. In order for the operating system to find the starting point of a partition, a map is required to be stored at the beginning of the disk. This map is called a partition table. When changes are made to the partitions, the partition table gets updated. In Linux, the raw disks are accessible using the /dev/sd ? Handle. The first disk is /dev/sda, the second disk is /dev/sdb, and the third disk is /dev/sdc, etc. In the illustration shown here, assume this is the disk /dev/sda. Then the three partitions will be visible to Linux as /dev/sda1, /dev/sda2, and /dev/sda3. Now let us look at a couple of problems with legacy partitioning. As shown in the picture, /dev/sda1 and /dev/sda2 are mounted on /x and /y respectively. Over a period of time when /y is full, /x may have a lot of space left, but it is not possible to dynamically adjust the size of the legacy partitions. Another problem with legacy partitioning is that a partition cannot cross disk boundaries. This is because the partition table on a disk has no knowledge of an outside disk. LVM is a high-level construct and so can manage slices from multiple disks. Here is an outline of how LVM works. LVM uses the legacy partitions or raw disk as building blocks to cluster them together and form a logical superdisk. Such a superdisk is called a volume group in LVM. Here is a different version of the visuals. The legacy partitions and the whole disk are used as building blocks to create a volume group. From the volume group, a slice can be carved out for creating file system. More concretely, here's what is involved. Partitions created on physical disk or whole disk by themselves can be made use of by LVM. Each one of the partitions or physical disks handed over to LVM is called a physical volume. A group of physical volumes can be combined to create a volume group. Such a volume group practically behaves like a logical superdisk. From a volume group, slices are carved out as logical volumes. A file system can be created on a logical volume and mounted on a mount point in Linux. These concepts are illustrated using 3 disks on Ubuntu 24.04. Here are the detailed steps. Each of these steps will be explained in the rest of the presentation. The first step is to identify and prep the building blocks for LVM. To make changes to the disk layout, the command fdisk is used. The disk /dev/sdb and /dev/sdd will have 4 partitions each. The partitions of dev sdb1, dev sdb3, dev sdd1, dev sdd3, and the whole of disk dev sdc will be used as the building blocks to create a volume group, superdisk. For illustration purposes, these are colored in green. To create those partitions on /dev/sdb and /dev/sdd as shown in the figure, the command fdisk is used. The terminal session is run as root. Do a grep for SD in the dmesg command. You will see info about disk. As you can see from the results, they are SCSI disk. So we can grep specifically for SCSI. Here you see the results about the 4 disks. The first disk is usually the root disk for Linux. /dev/sda will be left alone. To start, partitions are made in the /dev/sdb. The command is fdisk. First, take a look at the partition table. Use lowercase p to print the existing partition table. You can see that this is a DOS partition table. The command to see all options is lowercase m. As you can see here, there is another type of partition table called GPT. This is GUID partition table and it has some nicer characteristics compared to old DOS. It also works well with LVM. If you want to know more about it, you can Google GPT partition. In this case, the partition table is to be changed to GPT. The command is lowercase g. To create partitions, the command is lowercase n as in new. Every time you create a GPT partition, you have to specify the partition number, starting block, and size of the partition. We will create 4 partitions and write it to the disk. The first partition is 4 gigs, the second is 11 gigs, the third is 4 gigs, and the fourth is 4 gigs. The command lowercase w as in write is used to write the partition table from memory to disk. The dmesg command can be used to verify that the 4 partitions we created shows up. After prepping the building blocks dev sdb1, dev sdb3, dev sdd1, dev sdd3, and dev sdc, LVM can be given control of these as physical volumes, or PV for short. LVM will write some metadata on these building blocks. The command for creating physical volumes is pvcreate. Once the PVs are created, they can be combined to form a volume group, or VG for short. Every VG needs a name. In this example, the VG is called obidos. After creating a VG, it will show up under /dev. In this example, it will show up as /dev/obidos. To create a logical volume from a VG, the size and name of the LV must be specified. The LV in this example will be called data store, and the initial size will be 16 gigs. The command for creating LV is lv create. The size and name are specified using -L and -n arguments. A file system can be created on the LV. Since the LV is visible at the device level as /dev/obidos/datastore, it is possible to create a file system on it. Use the mkfs command on the device. Now the file system can be mounted. The directory /usr/local/obidos will be used in this example. Then use the mount command. In the future, if the LV has to be expanded, it can be done dynamically. It is not necessary to unmount the LV or shut down the server. Use the lv resize command to expand the LV. After the LV is expanded, the change must be communicated to the file system at the OS level. This is done using the resize 2fs command. Thank you for watching. Hope this was helpful to you.